All right, so let's go over the vector diagrams for these because this is really important that you know how to draw a vector diagram that's appropriate. So first of all, your vector should be acting on the same common point. There should not be extra diagrams to the side or anything. So all your vectors should be acting to this on the same object, usually on the center of mass. And these were drawn using the draw tool in shared Google Docs. So here we go. So for the first one, you have mass 1, which is lighter, less than mass 2. So mass 1 is going to go up. And with these two mass systems, you have to identify the positive direction, which is the direction that it's moving. So I show you that positive is up and that T is pulling it up and FG1, the weight of mass 1, is pulling down on it. So when you get ready to write the net force equation, that would be T minus FG1 equals M1A. So you always start with the net force equals MA. And since we're dealing with mass 1, M is M1 and FG is FG1. You want to make sure that you distinguish between those. So I was looking for a diagram that had T going up, FG going down, and the positive direction is up. And your net force is T minus FG1 equals M1A. In the second part of this, I wanted you to show me that this mass was moving down, so down is positive. And so it has tension on it and it has FG2. And in this case, it would be FG2 minus tension because FG2 is the force that's causing the motion. Tension is the force that's slowing it down. And that is equal to M2A. So that's what I was looking for in B. And then for the total mass system, then the tension is inside the system. So it's not part of it. And let me just backtrack. I want to make sure that you're not calling the force in a rope FA. FA is the applied force of you pushing or pulling on it. If you have a rope in there, the force is called tension. If you are physically pushing on it or pulling on it, then that's the applied force FA. It is also not the normal force, right? Normal force is a force that's only present when you're sitting on a surface. It's the surface that's supporting you. It's the support force, the surface on you, and it's called normal because it's always perpendicular to the surface. Normal means perpendicular. So when you do the total mass system, you're only looking at the two outside forces acting on it. And one of the outside forces is FG2 and one is FG1. So you should have an upward FG1 and a downward FG2. And in this case, the whole system would be moving downward, and so down is positive. So your net force would be FG2 minus FG1, and that is equal to the total mass times A, M1 plus M2. And most of you guys calculated everything correctly, so you did really good there. And in number 2, you're just pushing a mass that has friction on it. So you should have Fg and Fn, and you should have Fa, that's your pushing force, and you should have Ff, that's the friction. Friction always acts opposite the force that causes the motion. In number 3, you have an inclined plane. So in your inclined plane, you should always have the weight going down perpendicular. You should always have the perpendicular component of the weight and the parallel component of the weight. The parallel component of the weight goes down the incline. And in this problem, it said that there was friction acting on it. Okay, so in that case, you would want to draw friction going up opposite F parallel, and you always want to have the normal force opposite F perpendicular. If you did not have friction, then you would not have the friction force, but you would have the Fn, F parallel, F perpendicular, and Fg. In number 4, you're pushing the incline. You're pushing the mower. So the tension is angled down in the handle at an angle, and it has an X component that moves it forward and a Y component that pushes it into the ground. So when you draw that diagram, you need to show the X acting on the center of mass to the right and the Y acting on the center of mass in the same direction as the weight. And in that way, you'll know that the normal force is really equal to whatever the weight is plus Ty. And so that's going to change what the friction force is. So you want to make sure that you calculate the normal force correctly, because if it was just sitting on the ground, the normal force would be equal to just the weight. But since you're pushing down on it with Ty, the normal force has to counteract Fg and F and Ty, and then Ff would be mu times those two forces added together. In the next thing, you had a box on an incline, and you need to have Fg1 in that diagram. You need to have the perpendicular component of Fg1. You need to have the parallel component of Fg1. But this also had friction on it, so you need friction going on it. So why is it in the same direction as F parallel? Because this box is moving up the incline and F is down the incline. So notice I have two vectors going down the incline. That's FF and F parallel. I have Fn counteracting F perpendicular, and I have the tension pulling it up. So my net force equation would be tension minus FF plus F parallel. And that would make mass 1 accelerate. Your mass 2 is going down, so it looks just like mass 2 in number 1. It looks exactly like that. So there shouldn't be anything different in that scenario. It should be Fg2 minus tension equals M2A. And then the total mass is going to have two up arrows. It's going to have F parallel and FF. Those are slowing it down, and Fg2 is what's causing it to move. So the net force for that would be Fg2 minus F parallel plus FF. So to determine if this is going to rotate, you would want to know if Fg2 is bigger than FF and F parallel added together. If it is, then it will accelerate. And in number 7, you had a flat box on the table with friction. So it's got tension on it and friction on it, Fn on it and Fg1 on it. The net force for it would be tension minus Ft equals M1A. And the second mass is just like all the second masses, it's moving down. So it would have Fg2 and T on it. Its net force would be Fg2 minus T equals M2A. And then the net force, or the total mass diagram, once again, you have Fg2 driving everything, but in this case, FF is the only thing that is slowing it down. And that's basically what you have. Take a look, take the time to go over your answers and make sure that you get the right answers. Double check what you're doing, because I did not necessarily check all of your answers. I checked to see that you showed me all the work. I checked it, and I was really focusing on your diagrams, because the diagrams are something that you're going to need to be able to draw in this course, and if you can't draw them, you're going to be losing a lot of points on your exam. So make sure that you've got the diagrams under control.